When we introduced the model of the von der Waals gas to provide a better approximation of the behavior of real gases, we found that the equation of state of the model gas described by the von der Waals equation depends on parameters specific to real gases. However, we will show that the equation of state derived for von der Waals gases can still be cast in a universal form called reduced equation of state, which is the same for any substance in the von der Waals approximation. We already derived the relations between the critical constants and the von der Waals constants, and we saw that the critical temperature Tc of a von der Waals gas is equal to 8 times its pressure correction constant A over 27 times the gas constant R times its volume correction constant B. The critical pressure Pc of the gas is given by the constant A over 27 times the square of the constant B, and its critical molar volume V sub mc is equal to 3 times the constant B. We determine the critical compressibility factors EC of a von der Waals gas defined by the critical pressure Pc times the critical molar volume V sub mc over the product of the gas constant R and the critical temperature Tc, and found that it is equal to 3 over 8. We also express the von der Waals constants in terms of the critical constants, and we could write the pressure correction factor A as 3 times the square of the critical molar volume Vcm, times the critical pressure Pc. Similarly, the volume correction parameter was expressed by 1 over 3 times the critical molar volume V sub mc. The relationships between these two types of constants indicate that the critical constants completely determine the properties of a real gas in the von der Waals approximation, and they can be used to specify the behavior of the given real gas instead of the von der Waals constants. We therefore introduce a set of dimensionless variables describing the state of a von der Waals gas by normalizing its temperature, pressure and molar volume with their corresponding critical values. These dimensionless variables, called the reduced state variables of a von der Waals gas, are the following. The reduced temperature T are defined by the ratio of the absolute temperature T of the gas to its critical temperature Tc, is equal to 27 times R times B over 8 times A, times T. The reduced pressure P are defined by the ratio of the pressure P of the gas to its critical pressure Pc, is given by 27 times B squared over 8, times P. The third critical variable is the reduced volume V are defined by the ratio of the molar volume Vm of the gas to its critical molar volume V sub mc, and it is equal to Vm over 3 times B. By definition, the reduced variables measure the departure of the condition of the substance from its own critical condition. The later corresponds to the unit value of the reduced variables, and the deviation of these variables from one indicates that the substance is either in subcritical or supercritical state. Now we express the equation of state of a von der Waals gas in terms of the reduced state variables of the gas. The von der Waals equation states that the sum of the pressure P of the gas and its pressure correction constant A over the square of the molar volume Vm of the gas, times the difference between the molar volume Vm and the volume correction constant B of the gas, is equal to the gas constant R times the absolute temperature T of the gas. If we insert the formula for the constants A expressed in terms of the critical constants into this equation, then we can write the second term in the first parentheses as 3 times Pc times the square of V sub mc over the square of Vm. Similarly, the constant B in the second parentheses can be written as V sub mc over 3. After dividing this equation by the product of Pc and V sub mc, we obtain another equation stating that the sum of P over Pc and 3 times the square of V sub mc over the square of Vm, times the difference between Vm over V sub Cm and 1 over 3, is equal to R times T over the product of Pc and V sub mc. In the left-hand side we can apply the definitions of the reduced variables, and we can write it as the sum of the reduced pressure PR and 3 over the square of the reduced volume VR, times the reduced volume VR minus 1 over 3. In the right-hand side we express the ratio of R to the product of Pc and V sub mc in the fraction from the equation obtained for the critical compressibility factors EC, and write the fraction as 8 over 3, times the ratio of the temperature T to the critical temperature Tc. By applying the definition of the reduced temperature in the right-hand side, we arrive the reduced equation of state of the von der Waals gas stating that the sum of the reduced pressure PR and 3 over the square of the reduced volume VR of the gas, times 3 times the reduced volume VR minus 1, is equal to 8 times the reduced temperature TR of the gas. Or in another form, the reduced pressure PR is equal to 8 times the reduced temperature TR over 3 times the reduced volume VR minus 1, minus 3 over the square of the reduced volume VR. As a result, we obtained an equation of state for any von der Waals gas which does not contain the volume and pressure correction factors specific to the given substance. That is, the reduced equation of state is free from the von der Waals constants and is universal for all substances. The fact that the reduced equation of state is universal since it contains no constants specific to the particular substance allows us to establish a correspondence between the thermodynamic states of different media for which the reduced equation of state is equally valid. If we enclose some amount of different substances in two vessels labeled by the numbers 1 and 2, we can bring them into given thermodynamic states described by the temperature T, the pressure P and the volume V. The state variables of the corresponding substance are also labeled by 1 and 2. Because the substances are different, their critical constants are also different. For both the media we can define the reduced variables by the ratio of their state variables to their corresponding critical constants. In the general case, the state variables are not the same in the two systems, however it is possible to prepare the states of the substances such that their reduced variables are the same. If this condition holds, then we say that the two substances are in corresponding states. For example, first we can bring both of the systems into their own critical points described by their critical constants, and then change their thermodynamic states by holding one of their reduced variables equal to 1 and modifying the other two such that the substances could have the same deviation from their critical conditions. This can be achieved in a critical point apparatus where one of the state variables of the medium in the measuring cell can be kept constant while the other two can be modified, for example by applying an isothermal expansion or compression of the substance in its critical condition. In general, when two systems, either gases or fluids, are in corresponding states, they have the same set of the three reduced variables. Although their actual state variables may differ as seen in the example, the two substances are said to be in corresponding states if their reduced temperature, pressure, and volume are the same. In fact, the existence of a universal equation of state implies that if two reduced variables are the same for a set of the systems, then the third reduced variable is also the same throughout the set of systems. That is, they are in corresponding states with a pair of equal reduced variables from the complete triplet of variables. This condition can be formulated in one principle called the law of corresponding states in the following way. There exists a universal equation of state containing no arbitrary constants if expressed in the reduced variables describing the thermodynamic state of the substance. Hence, the law of corresponding state tells us if the two of the reduced variables, for example the reduced temperature and the reduced pressure, are given for a certain medium, we can solve the reduced equation of state for the third one, here for the reduced volume of the medium, which will be the same for any other substance at the same conditions given by the reduced pressure and the reduced temperature. In other words, substances at the same reduced pressures and temperatures have the same reduced volume. This is how von der Waals discovered the principle of corresponding states and stated that substances behave alike at the same reduced states. Because substances at same reduced states are at corresponding states, the law tells us that substances at corresponding states behave alike. As a result, in the von der Waals approximation, the thermodynamic behavior of all substances is essentially the same, except for a scaling factor that is related to the critical point of the substance. Critical constants become the scaling factor by which substances can be compared among each other in terms of their departure from criticality or their reduced states. If two substances are at the same reduced state, that is, they have the same relative departure from criticality, then the law of corresponding states demands that they behave alike regardless of their nature. In this case, we say that the two reduced states correspond to one another, and we expect that the substances at these states exhibit the same behavior. Here we present the isotherms of the reduced equation of state telling us that the reduced pressure PR is equal to 8 times the reduced temperature TR over 3 times the reduced volume VR minus 1, minus 3 over VR squared. The isotherms are shown for the reduced temperature in the range between 0 and 4 with the intervals of 0.1. The critical isotherm is represented by the red curve with the critical point K of the substance at the point of inflection of the isotherm, where the reduced temperature, the reduced pressure, and the reduced volume are equal to 1. As the equation of state shows, the reduced pressure is divergent at the reduced volume equals 1 over 3, that is at the excluded volume of the molecules comprising the substance in the hard sphere model. At absolute zero, where the reduced temperature vanishes, the reduced pressure of the substance is negative as it becomes inversely proportional to minus the square of its molar volume. Therefore, the isotherm at absolute zero is completely in the region of the mechanical instability, where the von der Waals equation of state cannot describe the behavior of the substance. This can be seen if we display the regions separated by the critical isotherm and the boundary curve of the mechanical unstable region. The green area represents the states of permanent gas, the yellow area covers the region where phase transitions can take place, and the orange area represents the mechanical unstable states where the von der Waals approximation breaks down. The correct description of the medium in this region can be obtained by applying Maxwell construction for the reduced equation of state. Even with this limitation, The pressure versus volume diagram plotted for the reduced equation of state is supposed to be universal for all substance, establishing the law of corresponding states. At the same time, the law of corresponding states is not always accurate due to the fact that the von der Waals equation is only an approximation, and the reduced equation of state does not always describe the exact corresponding states of real substances. In order to illustrate the law and its approximate nature, let us consider an example for the corresponding states of different substances. In the pressure versus volume diagram, we select the thermodynamic states A, B, and C in the vicinity of the critical point K, and the table shows the reduced variables in these three states. The point representing the state A is located on the critical isotherm, that is, the critical temperature Tr is equal to 1 in this state. The volume of the medium is chosen to be twice its critical volume, that is, its reduced volume Vr is equal to 2. Then the reduced equation of state gives 0.85 for the reduced pressure Pr. In the case of the state B, we hold the pressure of the substance at its critical value, that is, the reduced pressure stays unity, while we decrease the reduced volume from 1 to 0.6. This can be achieved by lowering the reduced temperature to 0.93 and evaluating the reduced equation of state at these subcritical values of volume and temperature. In the state C, the molar volume of the medium is held on its critical value, that is, the reduced volume is equal to 1, while the reduced temperature is raised to 1.1. For the slightly supercritical reduced temperature and the critical reduced volume, the equation of state gives 1.04 for the reduced pressure. Now we consider these three states in the case of two different substances, such as hydrogen and butane, for which we already presented the pressure versus molar volume diagrams in the discussion on the critical point of a von der Waals gas. By substituting the von der Waals constants of hydrogen into the equation of state, in this diagram we plotted a family of isotherms at given temperatures between 12 Kelvin and 92 Kelvin with the intervals of 2 Kelvin, where the critical isotherm is drawn in red color. We also saw that the critical temperature of the gas is equal to 33.3 Kelvin, whereas the pressure is given by 1.3 megapascal and the molar volume is equal to 0.0649 cubic meter per kilomole at its critical point K. For butane, the isotherms are derived from the von der Waals equation with the correction constants of butane and plotted between 165 Kelvin and 1105 Kelvin with the intervals of 20 Kelvin. The critical constants of butane were also presented before. Its critical temperature is equal to 425.2 Kelvin, its critical pressure is given by 3.8 megapascal, and its critical molar volume is equal to 0.255 cubic meter per kilomole. As in the pressure versus volume plot of the reduced equation of state, the green, the yellow, and the orange areas represent the regions of permanent gas, the mixed phases, and the unstable states in both diagrams. Now we introduce the states represented by the points A, B, and C on the pressure versus volume diagram of the reduced equation of state for both the substances. However, we need to modify some of the reduced variables shown in the table since there is some deviation between them and the solutions of the von der Waals equation containing parameters that are specific to the two substances. As mentioned before, this deviation is the consequence of the fact that the von der Waals approximation used to derive the reduced equation of state as a universal equation is not an exact description of the behavior of real gases. These two tables presenting the state variables of hydrogen and butane in the states A, B, and C illustrate the law of corresponding states and its approximate nature for the two species. The point A is located on the critical isotherms of the two substances, and in the thermodynamic state represented by this point both hydrogen and butane are at their critical temperatures, that is at 33.3 Kelvin and 425.2 Kelvin respectively. In this state both of the substances are confined in molar volumes that are twice their critical molar volumes, that is the molar volume is equal to 0.1298 cubic meter per kilomole for hydrogen and 0.51 cubic meter per kilomole for butane. The substitution of these values into the von der Waals equation containing constants specific for the two media, gives 1.22 megapascal for the pressure of hydrogen and 3.64 megapascal for the pressure of butane. By scaling the result with the critical pressures of the two substances, we obtain values of the reduced pressure that deviate from 0.85, the value specified in the table of the reduced variables. The superscript of 0.85 tell us that the reduced pressure of hydrogen is greater than 0.85 by 0.092 in the state A. Similarly, the subscript of 0.85 represents an increase of 0.101 in the reduced pressure for butane. As a result, if the two substances are in the state A, their reduced temperatures and their reduced volumes are the same, but there is a slight difference between their reduced pressures. Then hydrogen and butane in the state A have approximately the same reduced variables, or the two different substances are approximately at corresponding states. We have a similar situation in the case of states B and C. In the state B, the pressures of hydrogen and butane are kept at the critical values, while the substances are compressed into the molar volume 0.6 times smaller than the critical values. That is, they are confined in the molar volumes of 0.0389 cubic meter per kilomole and 0.153 cubic meter per kilomole, and the pressure of hydrogen is equal to 1.3 megapascal and the pressure of butane is given by 3.8 megapascal. The reduced temperature of the systems is specified to be 0.93 in the state B, from which we can compute the temperatures of the two substances in this state. If these temperatures and the molar volumes are substituted into the von der Waals equations of these substances, then they are supposed to give the critical pressure for both the systems. However, there is a deviation between the results and the critical values of the pressure, and we need to modify the reduced temperatures of the system so that we could keep the reduced pressure of the two media at unity. The decrease of 0.149 in the value of the reduced temperature equivalent to 26.1 Kelvin gives 1.3 megapascal, that is the critical pressure of hydrogen, when it is substituted together with the molar volume 0.0389 cubic meter per kilomole into the equation of state. Similarly, the reduced temperature decreased by 0.279 is equivalent to 277.9 Kelvin, and we obtain the critical pressure when we substituted this value and 0.153 cubic meter per kilomole into the von der Waals equation. As a result, the states B for hydrogen and butane are corresponding states, although only approximately, due to the small difference between the reduced temperatures of the two media. In the case of the state C, we hold the molar volume of the systems at their critical values, that is, the molar volumes of hydrogen and butane are equal to 0.0649 cubic meter per kilomole and 0.255 cubic meter per kilomole respectively. The reduced temperature is set to 1.01 for the two substances, which represents 33.6 Kelvin for hydrogen and 429.5 Kelvin for butane. If these molar volumes and temperatures are substituted into the von der Waals equations for the two media, then we obtain 1.46 megapascal for the pressure of hydrogen and 4.4 megapascal for the pressure of butane. By scaling these results with the critical pressures of the substances, we can also derive reduced pressures for them, which have some deviation from the value 1.04 specified for the state C. The reduced pressure of hydrogen is less than 1.04 by 0.083, whereas the difference is 0.119 for butane. Thus the reduced variables of hydrogen and butane are the same with a small difference in the reduced pressures in the state C, that is, the states of the two media with these reduced variables can be considered as corresponding states, at least approximately. We derive the reduced equation of state by substituting the von der Waals constants into the von der Waals equation of a given substance with its critical constants and express the result in terms of the reduced variables. Now we repeat the same procedure, but we do not replace all the state variables in the equation by their corresponding reduced variables. The von der Waals equation for a given medium states that the sum of the pressure P of the medium and its pressure correction constant A over the square of its molar volume Vm, times the difference between the molar volume Vm and the volume correction constant B of the medium, is equal to the gas constant R times the absolute temperature T of the medium. Here the correction constants of the substance can be expressed in terms of its critical constants as follows. The pressure correction constant A is given by 3 times the square of the critical molar volume V sub mc of the substance, times the critical pressure Pc of the substance, whereas the volume correction constant B is equal to the critical molar volume over 3. By substituting these expressions into the von der Waals equation, we can replace the von der Waals constants with the critical constants. If we factor out the product of P times Vm from the parentheses and divide the result by the product of R times T, then we obtain an equation stating that the ratio of P times Vm to R times T, times 1 plus 3 times Pc over P, times V sub mc squared over Vm squared, times 1 minus V sub mc over 3 times Vm is equal to 1. Because the ratio of the state variables to their critical values gives the reduced variable of the state variables, we can write the terms inside the parentheses as 1 plus 3 over the product of the reduced pressure PR and the square of the reduced volume VR, and 1 minus the 1 over 3 times the reduced volume VR. Since the first factor in the product in the left-hand side of the equation is the compressibility factor Z of the medium given by the product of the pressure P and the molar volume Vm over the product of the gas constant R and the temperature T, we divide the whole equation by the second and the third factors in the product and keep the compressibility factor Z in the left-hand side of the equation. As a result, we have a function in the right-hand side of the equation which depends only on the reduced pressure and the reduced volume of the medium. The result shows that the general form of the universal equation of state for the law of corresponding states is a function of the three reduced state variables of any substance. The ideal gas and the von der Waals gas are special cases providing explicit forms of this universal equation. The compressibility factor Z of any ideal gas is equal to 1, stating that it does not depend on the reduced variables of the gas in this idealized model. In fact, we cannot talk about reduced state variables of an ideal gas at all, since this model does not describe any critical phenomenon in the behavior of a real gas. The von der Waals equation of state already gives a more realistic description for the universal function, and as we have seen, the compressibility factor is a function of two reduced state variables of the von der Waals gas. Either it can be expressed in terms of the reduced pressure and the reduced volume, or equivalently in terms of other two pairs of the three state variables. However, the von der Waals equation of state is still an approximation applied to describe the behavior of real gases, and the general form of the universal function for the law of corresponding states can only be derived from the virial expansion of realistic equations of state constructed in statistical mechanics. In such an expansion, the compressibility factor Z of a real gas is expressed as an infinite series of negative powers of the molar volume Vm of the gas, where the coefficients C2, C3 and so on are known as the virial coefficients of the expansion. These coefficients are normally written in the form of coefficients dependent on the reduced temperature over the critical molar volume V sub mc. These temperature-dependent coefficients are computed up to an arbitrary order by applying the principles and methods of statistical mechanics. We can see that the first term in the right-hand side of the virial expansion is equal to 1, that is the zeroth order term of the series describes the ideal gas law. When we derived the von der Waals equation, we presented the virial coefficient in the second term in an explicit form depending on the temperature and the von der Waals constants. The first order term of the virial expansion therefore describes the von der Waals approximation. In the case of real gases, we also need to determine higher virial coefficients to provide a better description of their behavior. When we introduced the compressibility factor of real gases, we mentioned that the principle of corresponding states providing the general description of the behavior of real gases in terms of their reduced state variables, allows us to determine their compressibility factor efficiently with relative high accuracy. We saw that the graphs of the compressibility factor versus the pressure at given temperatures for various species such as hydrogen, nitrogen, and oxygen are very different. However, if the compressibility factor of different substances is plotted against their reduced pressure at a given reduced temperature, then the data points are scattered around the same curve in the Z versus PR diagram, as seen in the figure. The measured values of the compressibility factor versus the reduced pressure are plotted for 8 different substances from methane to water at reduced temperatures between 1 and 2 with the intervals of 0.1. The curves at given reduced temperatures shown here are results of the curve fitting with the measured compressibility factor of hydrocarbons. Because of this general feature, generalized compressibility factor charts can be used for many different substances in accurate thermodynamic calculations, which express the compressibility factor as a function of pressure and temperature. The most commonly used chart has been the Obert-Nelson chart, which is compiled from hundreds of data points of 25 or more different pure gases, achieving an accuracy within 1 or 2% for the compressibility factor greater than 0.6, and within 4 or 6% for Z values between 0.3 and 0.6. The parameters used in the Obert-Nelson chart are the standard reduced variables, that is the reduced pressure P are given by the ratio of the pressure P of the gas to its critical pressure Pc, the reduced temperature Tr of the gas given by the ratio of its absolute temperature T to its critical temperature Tc. The third state variable of the gas is its pseudo-reduced volume V are defined by the specific volume V of the gas over the ratio of the specific gas constant Rs of the gas times the critical temperature Tc to the critical pressure Pc. As shown here, the Obert-Nelson compressibility chart is normally presented in the form of several plots covering different ranges of the reduced pressure. The first plot contains the Z versus PR charts represented by the red curves for the reduced pressure from 0 to 1, and also includes a chart for the compressibility factor at very low reduced pressures between 0 and 0.1. The curves are plotted at the reduced temperatures between 0.6 and 5.0. The chart also has a family of blue curves representing the compressibility factor as a function of the reduced pressure at constant pseudo-reduced volumes in the range between 0.7 and 8.0 in the full chart and between 9 and 30 in the small one. The second plot of the generalized compressibility chart shows the compressibility factor as a function of the reduced pressure between 0 and 7, covering the domain of the critical point for the reduced variables. The range of the reduced temperature for the red curves is defined from 1.0 to 5.0, whereas the blue curves are plotted at the pseudo-reduced volumes between 0.2 and 3.0. The third plot of the generalized compressibility chart covers the widest range of the reduced pressure between 0 and 40. The chart shows the red curves plotted at constant reduced temperatures between 1.0 and 15, whereas the blue curves represent the compressibility factor at the pseudo-reduced volume in the range between 0.105 and 0.6. If we want to determine the compressibility factor of a given substance of known critical constants at a given temperature and pressure by using the compressibility chart, we need to complete the following steps. First, we compute the reduced variables of the substance from its given state variables and critical constants by applying the definitions shown here for the parameters of the plots. Then we find the reduced pressure on the x-axis of the chart. From there, we move up on the chart along a vertical line until the red curve at the given reduced temperature is found. From the intersection of the vertical line and the curve, we move right along a horizontal line until we reach the y-axis. The intersection of the horizontal line and the y-axis gives the value of the compressibility factor at the given temperature and pressure of the substance. As an example illustrating this procedure, we chosen carbon dioxide from the list of substances for which the compressibility data is plotted against the reduced pressure. If we consider a vessel filled with 100-liter carbon dioxide at the pressure of 6 megapascal and at the temperature of 30 degrees Celsius, that is 303 Kelvin, then we find that the reduced pressure of the gas is 0.81 and its reduced temperature is close to unity, since the critical pressure of the gas is 7.39 megapascal whereas its critical temperature is given by 304.2 Kelvin. Then we draw a vertical line from the point on the x-axis at 0.81 up to the curve plotted to the reduced temperature equals 1, and a horizontal line from their intersection to the y-axis. The horizontal line intersects the y-axis at the point 0.62, that is the compressibility factor Z of the 100-liter carbon dioxide at 6 megapascal and 30 degrees Celsius is given by 0.62. Instead of the reduced temperature, we can also use the pseudo-reduced volume of the substance to determine Z in the same way by using the blue curves. When we look at the compressibility charts, we confirm the following information. At very low pressure, that is where the reduced pressure is much smaller than 1, real gases have a compressibility factor close to 1, indicating that they behave like as an ideal gas regardless of their temperature. With increasing temperature, that is where the reduced temperature is greater than 2, the compressibility factor of real gases has a moderate deviation from 1, and their ideal gas behavior can still be assumed with good accuracy. In the vicinity of the critical point where the reduced variables are equal to 1, the compressibility factor of real gases has the greatest deviation from 1 at reduced pressures less than about 10, that is, they have the greatest deviation from the ideal gas behavior. Besides this deviation in the critical region, the accuracy of the chart is limited close to the critical point due to the sensitivity of the compressibility factor to the reduced pressure and temperature. The values predicted by compressibility charts have also very large deviations from the measured values for highly polar gases due to the strong intermolecular forces between the polarized molecules. In the case of hydrogen, helium and neon, the reduced pressure and temperature must be modified at critical temperatures above 5 by scaling the state variables with the critical constants +8, so that one could use the general compressibility charts for such gases.